Hi everyone. My name is Shuichi Tsutsumi, and thank you for coming to my session. This is my GitHub page. To give you my personal background, I am an iOS engineer working for a startup named Fusion in San Francisco, and originally from Japan 1 year ago. I've been developing iOS apps for almost 7 years now, and every year when the new iOS version is announced, I create a collection of code examples for the new iOS APIs and publish them as an open source named iOS sampler. Those are widely used by developers. So in this session, I will talk about the implementation of deep learning feature which can work on iOS devices. To do that, there are some related frameworks in iOS SDK. I'll also explain how to choose the frameworks and how to use them. First, let me explain why deep learning on iOS is so exciting. Recently, we hear news related deep learning almost every day. For example, self-driving car experiments on public roads have started, or AI named DeepMind made by Google beat a Go champion, or a cancer detection system using deep learning can work better than human doctors, and so on. But these examples might look too big projects, so I'll introduce some more examples of applications which use deep learning. This application is named AutoDraw. It converts your rough sketch to a well-designed drawing. This is pose estimation. It can recognize human skeletal pose. Considering how many things have been brought to apps by face recognition, I think this pose estimation also can have many possibilities. As another application example, our research says it can synthesize a frontal face from the profile. This picture shows one of frontal faces is the generated one from the side face, and another one is the real one. This Hair paper says it can generate a 3D model of a hairstyle from a single image. There are even more examples. However, what I want to say here is now such an evolutional technique is available on iOS. So that's why I titled this talk Deep Learning on iOS. It means that deep learning can work on iOS devices. I'll show a demo. Sorry. Okay, this sample app can recognize 1,000 kinds of objects. For example, now it recognizes notebook, or laptop or keyboard or even spacebar, or I bring this coffee cup, coffee mug, or this Hayat ballpoint pen, or my iPhone, or so it can recognize many kind of things in real time. And so please look at the. Can you look at the status bar? Now it's. Please look at the status bar. It's working on airplane mode, so it means this sample is working offline. So, okay. Because the sample app working offline because this sample has a pre-trained neural network and it's working on the device without calling backend APIs. Please imagine if this app uses backend APIs for the real-time image recognition, it must send each frame image and receive the result 60 times per second. So it cannot be used with per network, and the server load will be very heavy. In addition, the load increases in proportion to the number of users. If the app can work offline, it will be more useful. As you know, Google Translate app has a real-time translation feature, and it's very helpful. But when I lived in Germany for a month, I wanted to buy toothpaste in a supermarket, and deep inside the supermarket, the connection was very bad, and I could not use the app, and it made it difficult for me to choose toothpaste. If the translation could work offline, it would be more useful. Okay, here you might ask a question. Deep learning requires very strong computing power. Are mobile devices strong enough? They seem too weak, even though they are rapidly improving. That's true. Deep learning requires strong computing power when it's training. However, regarding inference, using the trained model, the computation is not so heavy, so it can be processed even on mobile devices. So, machine learning related frameworks in iOS focus on inference using pre-trained models. Okay, I have talked about why deep learning on iOS is so important. Now let's get started the implementation. As you know, a machine learning framework, Core ML, has been introduced in WWDC 17. In WWDC 17, the largest hole was 100% full for the Core ML session. I was surprised that so many developers are interested in Core ML. But wait a moment. Let me tell about the relationship of the machine learning related frameworks before starting to explain about Core ML. Here is CoreML. Vision framework helps to use CoreML models from your app. And CoreML uses CNN APIs in MetalPerformanceShaders framework and BNNS in Accelerate framework below it. CoreML and Vision have been introduced in iOS 11, and the lower layer APIs were introduced in iOS 10. Now, if we do not use these iOS 11 frameworks, it still works. Of course, it's optimized for the GPU and CPU because these are MetalPerformanceShaders framework and Accelerate framework. And of course, it's available for iOS 10 too. Not only iOS 11, like CoreML. In addition, the same as CoreML, basically any third-party machine learning tools can be used to train the models, such as TensorFlow or Keras. I'll explain about this later. So it's a good thing to start the implementation using these iOS 10 frameworks. After this, I'll tell about CoreML. MPS-CNN work on GPU with Metal, and BNNS work on CPU. When the network is small, BNNS might be better, but in many cases, GPU is better for neural network calculations. So let's start with MPS-CNN. When you start to learn about MPS-CNN, you might find a problem. It's difficult to find practical information for MPS-CNN. For example, it hits only 900 results with keywords for MPS-CNN, even now. Meanwhile, it hits about 160,000 results for CoreML, even though only 2 months has passed since it was announced. So, at first, finding the method for the implementation was a bit hard because of limited information. But once I figured it out, I realized it's actually very simple. I'll explain it with 3 steps. Step 1 is creating the model. As I already mentioned, iOS machine learning frameworks runs the inference using pre-trained parameters. So, main topics for this training step are which tools can be used for the training, and what kind of format can be used to pass the pre-trained parameters to MPS-CNN. Actually, any third-party ML tools can be used for training, and any model format can be used. In detail, for example, Apple's sample uses .dat files. They are common binary files, so not specifically for iOS or MPS. It contains the trained weights and biases as binary data. So it means that we can use any other format as long as it can be read by the iOS app, such as HDF5. HDF5 is a file format which can be exported from Caffe or Keras, and it can be read from iOS. For this reason, I said we can use any kind of any third-party machine learning tools as long as it can train CNN and export the trained parameters. So we can use Caffe, Keras, TensorFlow, and so on. Next step is implementing the network. This is an example of a convolutional neural network. Let's assume we want to use this network. MPS has a class named MPS CNN convolution to implement this convolution layer. And also there is a class named MPS CNN pooling to implement this pooling layer. And convolution, pooling, convolution, and there is MPS CNN fully connected class to implement this fully connected layer. So there are already classes corresponding to each CNN layers in MPS. The names are almost the same, like convolution, MPS CNN convolution for convolution layers, so we can easily find the class to be used. And the complicated math or GPU optimization are encapsulated. So we don't need to touch these difficult parts by ourselves. Then we can run the inference. This inference step is simple. First, convert the input image to MPS image. This MPS image is a class to handle image data in MetalPerformanceShaders framework. Then input it to the CNN, which we implemented in step 2. And the CNN has loaded the trained parameters which we created in step 1. Then the CNN outputs the results of the inference. And we can do something using the results. To recap, there are the 3 steps for the implementation. Step 1 is creating the model. Any machine learning tools can be used, and any file format can be used for the trained parameters. Step 2 is implementing the network. Classes corresponding to each CNN layers are already provided by MPS CNN. Step 3 is implementing the inference. Input an image to the CNN and output the results from the CNN. It looks simple, right? As a trial, I created a sample app which detects a logo using the custom model. At first, I collected these training data. There were about 86 logo images. The training data is too few, so I increased each data by 70 times by adding some changes after cropping it. They might look almost same, but you can see some of them are a bit rotated and some of them are slightly translated. Then I trained the model using TensorFlow. TensorFlow has a function to export the trained parameters as binary data. So this is the sample up, and now it doesn't detect anything, and here I have Swift logo, and okay, so it detects Swift logo. Of course, it's still working airplane mode, so it means it's working offline. And this device iOS version is iOS 10 because I use MPS-CNN framework. If it's CoreML, we can't use on iOS 10. Okay, so far I have explained how to implement a deep learning feature using MPS-CNN. It looks simple and works well, but of course it's not perfect. Please look at this image. This is the network for the logo detection. Although I customized this a bit for my Swift logo detection, it's almost the same. And this is the network named GoogleNet. It's much more complicated than the logo detection network. The GoogleNet is used for the inception model, and the inception model is the network which is used in this image recognition sample. This sample is based on Apple's official sample code. So let's see the Apple's implementation of the GoogleNet in the sample. Okay, this is the sample code, and so this source code is my iOS sampler, but this image recognition sample is basically come from Apple's official sample, and this class file is the implementation of GoogleNet. So let's see. So it has many convolution layers, and this slim MPS-CNN convolution is a wrapper of the MPS-CNN convolution, and there are so many convolution layers. So still implement, yes. So this implementation is there are 2,000 lines only for the network, only for the GoogleNet. So I mean, so to implement this network using MPS-CNN, we need to write 2,000 lines only for the network, according to the official sample. So here, Core ML has been introduced in iOS 11. Please look at this flow. This is the development flow with MPS CNN. We need to write code to extract the trained parameters from the model file. Then we need to write code to parse the binary files. Then we need to write code for the network. Sometimes this code becomes very complicated. If we use CoreML to use the same custom model, this flow becomes much simpler. After the training, at first, convert the model to a ML model file using CoreML tools. Then, drag and drop it to the Xcode project. Then, related classes are automatically generated. That's it. So, actually, we don't need to write code to parse the trained parameters or to construct a complicated CNN anymore. In MPS, there is another difficulty. When inputting an image to the CNN or getting the result of the inference from the CNN, we need to handle them with Metal. If you are familiar with Metal, it will not be a difficulty. But most of iOS developers or machine learning engineers don't have enough experience to use Metal. You might think these codes don't look so difficult, but we also need to care about how the implementation is efficient for GPU and CPU. For example, passing data frequently between CPU and GPU might be a bottleneck. But in iOS 11, we can use this vision framework too. Using vision, we can pass the input image as a shear image, or we can get the results very easily from classes of the vision. We don't need to touch Metal layer. So, although this works, CoreML and vision makes it much easier. Okay, so far I explained how to implement deep learning feature without iOS 11 frameworks and with iOS 11 frameworks. Here, you might have a question. How about BNNs in Accelerate framework? As you know, Accelerate framework is a library of mathematical computations and image calculations optimized for CPU. I had the same question. In my understanding, deep learning is suitable for being computed on GPU. Our research says, for training AlexNet, CPU took more than 40 days, and GPU took less than 6 days. So I wonder what kind of cases BNNs is suitable. So I asked at Metal Labo in WWC 17, how can we utilize both MPS, CNN, and BNNs? The Apple person answered, basically use MPS CNN because it works on GPU. Oh, okay, but when should I choose BNNs? I asked again. He answered, I don't know. Okay, that was just a conversation, not an official answer. He also said later, WatchOS might be a case on that you should use BNNS. Because WatchOS doesn't support MPS-CNN, but supports BNNS. I haven't tried yet. I also discussed with some people about this, and I currently understand like this. The cost for passing data between CPU and GPU is not small. When the network is small, the CPU and GPU communication cost might be bigger than the benefit of parallel processing for the network. So BNNS might be better option than MPS-CNN when the network is small. But I'm sorry, I haven't tried it so much, so I can't say concretely how small it should be. Okay, to recap, first, I explained why deep learning on iOS is so exciting. Then, I explained how to implement it. And in iOS SDK, there are some frameworks to implement the deep learning feature. So first, I used only MPS-CNN, which was introduced in iOS 10. And then I explained how CoreML and Vision makes it simpler and easier. Also talked about when to choose BNNS. Thank you very much for your time. So if you have questions, please speak slowly. Do you have a question?
What is the impact to app sizes by including?
Oh, app size?
Yeah, app sizes. So
Binary size?
one thing about that now is a gig,
Yeah, so I haven't actually I haven't correctly measured, but for example, that is the big limitation of this this feature currently. So the model becomes very big, like 100 megabytes, 500 megabytes, and so, but it can be compressed when it's built. But I don't measure how it becomes smaller. But the model easily be few hundred megabytes. And for example, my Swift logo detection models has 500 megabytes. Even only detects Swift logo. Yeah, maybe it can. I can make it smaller, but now it has 500 megabytes, and it also uses big memory. So it works on iPhone 7. iPhone 6s is still okay, but on iPhone 6 sometimes not enough memory. Yeah. Is it okay?
Yeah, I mean, if you had additionally any techniques or tips.
Oh, yeah. Techniques? Oh. So your question is how make the model smaller, right? So I'm not a machine learning professional, but there are. So in my knowledge, there are some way to reduce the model size. For example, we can reduce the number of features, number of dimensions of the features. Like, so, for example, I use 4,000 feature channel for safe logo detection, so it can be reduced until by 500 or something, and I think it will still work. And yeah, so the parameters are reduced, so the model size will be smaller. Yeah. Any other question?
You know what kind of convolutional neural networks are appropriate for counting objects, counting small objects?
Counting small object. Sorry, actually I don't know what kind of network would. So your question, sorry, I repeat it. Your question is what kind of neural network is suitable for counting small objects?
Yeah, where you know the geometry of each object.
Sorry, geometry of each object?
So if I had lots of small objects and I knew exactly the geometry of those objects, I knew exactly how small they were, the length of each of them, the height of each of them, I know I've got lots of them scattered out.
Okay, so for example, there is a popular network named YOLO network, and it can detect trained object, and it can also specify the place in the image, so we can know how many objects in the image. So I think we can use YOLOnet for that case.
Thank you.
So if you have more questions, please talk to me later. Thank you.
Are you going to make the resources you provided, like the code and slides, available?
Oh, sorry?
The slides and resources, the code?
Yeah. I upload at least this slide.
Okay.
The model is super big, so not good for GitHub. And yeah, so the code is basically come from the Apple's sample reference, so similar to Apple's sample. So I think, yeah, I might upload the code later, but basically so I already upload the iOS 10 sampler, and it includes the two samples which use MPS CNN, and one is detecting handwriting numbers, handwriting digit, and another is the image recognition sample. It will be enough for reference. And I also upload the slide.
Okay, thank you.
Okay. Thank you. Thank you very much.